All right, this is going to be our walkthrough for the assignment titled Basic Applications of the Derivative. So in this assignment, we're going to be asked to find all of the extrema, identify any that are absolute. We're also going to have to list all of our intervals when it's increasing and decreasing, find the intervals when the function's concave up and concave down, and also find all the points of inflection. So we're going to have to deal with the first derivative and the second derivative for this. So step one here for x squared minus 8x plus 16 is to just think about what the domain is. This is a polynomial function, so its domain is going to be all real numbers. So we don't have any inherent restrictions that we have to deal with. So then we'll just go right ahead and take the derivative, which is just 2x minus 8. That's never undefined, right? F prime is never undefined, so we'd want to make a note of that. We'll say f prime never undefined. And then we'll say it equals 0. Well, it equals 0 when x is equal to 4. So we only have one singular critical value at x equals 4. We'll come back and we'll do the sign chart for that right now. So if we do x equals 4 for f prime, if I plug in something more than 4, like a million, we can see that 2x minus 8 evaluates to be a positive. And if I plug in something less than 4, like 0, it evaluates to be a negative, which tells me that f goes from decreasing to increasing at x equals 4. So that tells us right away what our locations of our only extrema at x equals 4 is. And it also tells us when the function's increasing and decreasing. In fact, let's just find f of 4 right now so that we've already taken care of that. F of 4 ought to be 16 minus, that'd be 4 squared, minus 8 times 4, which would be minus 32, plus another 16. Right, so f of 4 is just going to equal 0. So we've kind of taken care of that. And we know that this is a quadratic. We know it's a parabola. So we know that the end behavior of this function is going towards infinity on both sides. Right, so we want to think about that because we have to determine if the extrema are absolute extrema. And if this thing says it's increasing forever after 4, or it's been decreasing forever from negative infinity, that doesn't necessarily guarantee that it's an absolute extrema there, right? Because, well, actually, in this case, it does guarantee that that one's an absolute extrema. But if we had like another turning point here, we wouldn't be certain that there was actually an absolute extrema at one of those values. We'd have to see what's going on if there's asymptotes, horizontal asymptotes. But this one doesn't have any, so we don't really need to worry about that. So after we've got our first derivative, we'll now find our second derivative. Our second derivative is just the derivative of the first derivative, right? The derivative of 2x minus 8 is just 2, which we know is never undefined, and we know it never equals 0, right? So there aren't going to be any points of inflection, right? It does not equal 0, and f double prime is never undefined. And so since 2 is greater than 0, we know that f is always concave up because the second derivative is always positive. So really, actually, we're ready to finish up this problem. We've kind of got all the information we've needed. So we'll write out, first of all, that it has a local, which is also the absolute minimum, 0 at x equals 4. We have no local or absolute max because our sign chart shows there was no maximum. Okay? We know that we are increasing on the interval from 4 to infinity, and that we are decreasing on the interval from negative infinity to 4, and that we are always concave up. So we'll say that we're concave up from negative infinity to infinity. We will say that we are never concave down, and that we have no points of inflection. And that ought to cover all of the things that we were asked for in this first problem. Our next one here, we're just going to follow the exact same process. Same question, except different function. So we'll take our derivative. The derivative of 1/3 x cubed is just x squared, and the derivative of minus 2x squared is minus 4x. We'll again note that there's no domain restrictions on the original function. and that f prime is never undefined. These polynomial ones make that pretty easy. Nothing too weird to worry about. And then we'll set this equal to 0, which allows us to factor out the x. And we can see that we have critical values of x equals 0 and x equals 4. And so we'll make our sign chart with just those two values, x equals 0 and x equals 4. And we'll test some things into our factored form of our derivative to see if it becomes positive or negative. So if I plug in something between 0 and 4, like 1, we end up with a positive 1 times a negative 3, which is a negative. If we plug in something more than 4, like a million, we get a positive times a positive, which is positive. And if we plug in something less than 0, like negative a million, we get a negative times a negative, which is also a positive. So we can be guaranteed that our function goes from increasing to decreasing to increasing. And also that we do need to know what f of 0 and f of 4 both are. So f of 0 is just 0, right? That's easy to plug into your original function. F of 4, though, is a little more difficult, right? F of 4 is going to be 4 cubed, which is 64, over 3. And then 64 thirds minus, well, 4 squared is 16 times 2 is 32. And if I get a common denominator on that, I'm going to do 64 thirds minus 96 thirds, and 64 thirds minus 96 thirds is just going to be negative 32 thirds. So there's our local max and our local min. We'll come back and write those all at the end. But first we'll do our second derivative. So our second derivative here is going to be f double prime of x is just the derivative of x squared minus 4x, which is 2x minus 4. That's, again, never undefined, right, because it's just a polynomial function. But f prime does equal 0 when 2x minus 4 equals 0, or when x is equal to 2. And I'm going to just note that this sign chart here was for f prime, because I'm going to have a second sign chart. I don't want to get confused. So when I put x equals 2 onto my sign chart for my second derivative, I'll just plug in something greater than 2 to 2x minus 4, like a million, and see that I get a positive, which tells me that this is concave up, okay? That the function is concave up. And if I plug in something less than 2, like 0, I get a negative, which tells me that f is concave down. And it tells me that since there's a change in concavity, there is a point of inflection at x equals 2. So we'll need to find f of 2. So f of 2 is going to be 2 cubed, which is 8 over 3. And then it's 8 thirds minus 2 times 2 squared. So 8 thirds minus 8. Well, if I multiply that by 3 over 3, I have 8 thirds minus 24 thirds, which is negative 16 thirds. So we should be able to list out all of the information that we needed for this one. We had, our function had a local, we should have also gone in through here and talked about whether they were local or absolute before we write this out, because it does say identify if they're absolute. We know this is a cubic, which means that this is going down here to negative infinity and up to positive infinity, which means that we're not going to have any absolute extrema. So all we have is local extrema. So we have a local min, and our local min was negative 32 thirds at x equals 4. And we had a local max of 0. And that was at x equals 0. And our function, if we look at that sign chart again, we can see that our function was increasing from negative infinity to 0 and from 4 to infinity. So we're increasing from negative infinity to 0, union 4 to infinity. And we were decreasing on the interval in the middle. So we were decreasing from 0 to 4. We were concave up. If we look back at our second derivative sign chart, we were concave up from 2 to infinity. And the College Board always wants the concave up and concave down intervals with parentheses no matter what, unlike the increasing and decreasing ones. And we were concave down from negative infinity to 2. And then we had our point of inflection, and our point of inflection was the 0.2 comma negative 16 thirds. And so that should be all the information that was asked for in that second one. So now we'll take a look at this one, a little bit more complicated function, the natural log of x squared minus 1. So the first thing that we're going to think about for this one, because it is a more complicated function, is what's the domain of this function? Well, we can take the natural log of only positive numbers. So we need to know when is x squared minus 1 greater than 0. Now we can solve this as just like a regular old quadratic inequality, but if you're not comfortable with that, you can always factor it and say I need x plus 1 times x minus 1 to be greater than 0. You just make a sign chart for your original function, putting negative 1 and 1 on there because those are the roots of this function. And we test numbers in between negative 1 and 1, less than negative 1 and greater than 1 to see when this function is actually greater than 0. So if we plug in something like 0, we can see that we end up getting a negative, right? Because we get a positive 1 times a negative 1. If I plug in something more than 1, like a million, I'll have two positives multiply together. And something less than negative 1, like negative a million, I'll have two negatives multiply together, which is a positive. Well, we wanted the values when x squared minus 1 was greater than 0. So that's going to be a domain for us of negative infinity to 1, and then 1 to infinity, right? The two sections where we got positives, not the section where we got negatives. So we have a big gap in our graph between negative 1 and 1. Okay? Forgot that negative there for a second. We got it in there. So when we make our sign chart, we're going to just leave a big gap in the middle for negative 1 to 1 when we do the sign chart of the derivative. So that's what we're up to next, is now working with our derivative. So f prime of x, since this is natural log of u, is going to be 1 over u. And then we'll multiply that by the derivative of u, which will just be 2x. The values that make the denominator equal to 0, right, the things that make f prime undefined, are negative 1 and 1. But negative 1 and 1 are not in the domain of our function. So it's undefined never on our domain of our original function. So I don't need to worry about those. And we already talked about the fact that we're going to put those negative 1 and 1 values into our sign chart anyway, right, because we're going to have this big gap in the middle. So then we just look for when is f prime of x equal to 0. That'd be when 2x is equal to 0, which is when x is 0. So we'll make a sign chart. Well, actually, we don't even have to worry about x equals 0. And because x equals 0 falls not in our domain, so we don't really actually have any critical values that are within our domain, right? Critical values have to be in our domain. So we will still make our sign chart, right, for our first derivative, but we're just going to put negative 1 and 1 on here. I kind of put an x in the middle because this is not in our domain. Right? And we can determine if the function is increasing or decreasing on either side of this by just plugging the numbers into our derivative. So if I plug in something more than 1, like a million, into my derivative, the top is going to be positive and the bottom is going to be positive. So this is going to be positive. And if I plug in something that is less than negative 1, like negative a million, the top is going to be negative, but the bottom is going to be positive. So we'll get a negative, which will tell us that this function goes from decreasing, and then it has its giant discontinuity, and then it goes back to increasing. Right? So f decreases, and then f increases, and we found that from our first derivative sign chart. So next step is going to be to find when this thing is concave up and concave down. So we're going to find our second derivative. So our original derivative here was just 2x over x squared minus 1. So we'll use the quotient rule to find this derivative. So f double prime of x is going to equal, quotient rule would be denominator times derivative of numerator, which is just 2, minus numerator times derivative of denominator. And that'll all be divided by our denominator squared. So if we simplify this out a little bit, this is a 2x squared, and this is a minus 4x squared, which is going to give us a negative 2x squared in the numerator. And then we have the minus 2 right here over x squared minus 1 squared. And once again, the denominator of this is never going to give us any undefined values that are on our domain, on that domain of f. So I don't really need to worry about that because it's just that same denominator again. But the numerator, we'll need to look at that. So negative 2x squared minus 2, if we set that equal to 0, we end up seeing that, well, that becomes x squared is equal to negative 1, which we know has no real solutions. So we can see that there's not going to be any points of inflection for this either. And all we really need to do then is we need to make a sign chart for our second derivative. Again, just putting negative 1 and 1 on and xing out that part in the middle because that's not part of our domain. And if I plug something more than 1, like let's say 1,000,000 into my second derivative, this numerator here is going to be very negative and my denominator will be positive, so I'm going to be concave down. And if I plug in something like negative 1,000,000, the same thing is going to happen, right? Because there's going to be this negative sign out in front. So this function is going to be concave down on its entire domain. And so we've got no maxes, no mins, no points of inflection because we didn't have any critical values or any values that made our second derivative 0 or undefined on the domain. And we've got our intervals where we're increasing and decreasing and concave down only. So this function is increasing from 1 to infinity, right? And that's all we had for our sign chart, and decreasing from negative infinity to negative 1, right? If we look back to that sign chart, we decreased from negative infinity to negative 1 and increased from 1 to infinity. We were concave down on our entire domain, right, which was negative infinity to negative 1 and 1 to infinity. We were never concave up. And we had no local or absolute max or min. And we had no points of inflection. All right, for our next one here, it's going to be the exact same process that we've been doing. So first off, we think about the domain. The domain here is going to be all real numbers because this is a polynomial function. But we do need to take a derivative here. So f prime of x is going to be 4x cubed minus 36x. We'll set that equal to 0 because we know it's never going to be undefined, right? We'll say f prime is never undefined. Make a note of that. It's always good to do. We'll factor out the 4x from this, giving us 4x times x squared minus 9 equals 0, which is the same as 4x times x plus 3 times x minus 3, giving us 3 critical values, 0, negative 3, and positive 3. And so we'll immediately make our sign chart for these. Right? So we got negative 3, 0, and 3, all for f prime. And when I plug in some numbers here, let's say something between 0 and 3, like 1, we end up with a positive from the 4x, a positive from the x plus 3, but a negative from here. So 2 positives times a negative makes a negative. And one thing we might note is that since the multiplicity of each of these roots is 1, we're just going to flip back and forth between positive and negative for all of these. But we'll test numbers just to be certain. If I plug something more than 3 in, like 1,000,000, I get 3 positives, right? All of those become positive. Something between 0 and negative 3, like negative 1, we get a negative for the 4x, but a positive for the x plus 3, and then another negative. So 2 negatives make a positive. And then something less than negative 3, like negative 1,000,000, they all become negative, and 3 negatives will be a negative. So we can see that our function decreases, increases, decreases, and then increases. That's what f is doing. So we will need to find f of negative 3, f of 0, and f of 3. F of 0 is pretty straightforward. Just plug in 0 to the original function and you get 0. To find f of 3, well, again, you're just going to plug in 3. So f of 3 is going to be 3 to the 4th power. 3 to the 4th power is 81. We have 81 minus 3 squared is 9, and 9 times 18 is 162. So that comes out to be negative 81. And if we put in negative 3, we're going to get 81. And then we're going to get the same thing, minus the 162 is, again, negative 81. And one thing to note here is that we can see that this is going up towards infinity, and this is going up towards infinity. So we can be, because we know it's a 4th degree function, right? That's what polynomial functions do, is they either approach infinity or negative infinity at the ends. So we know that we're not going to have any absolute max, right? This value at 0 is not going to be an absolute max. But the values at 3 and negative 3, the negative 81s, since they're the same, the absolute minimum is going to be negative 81. So the next thing we need to do, the next step here is going to be to take the second derivative. So we had f prime of x was equal to 4x cubed minus 36x. So we'll find f double prime of x, which is going to be 12x squared minus 36. Again, f double prime is never undefined, but it does equal 0. We can factor the 12 out if that makes things a little bit easier to look at here. We have 12 times x squared minus 3, or x is equal to positive or negative root 3. So we've got two values to put onto a sign chart for the second derivative here, negative root 3 and positive root 3. So we'll plug those into our second derivative. Something between those would be 0, which is just going to give me a negative here, telling me that f is concave down. And again, the multiplicity of each of those roots is 1, so I know it's just going to swap each time. But if we do plug something more than root 3 in, like a million, we can see that our second derivative is positive, and we are concave up. And the same will happen with negative a million. We'll end up with a positive, and we'll be concave up. So our original function, right, f of x was x to the 4th minus 18x squared. So if we evaluate that at negative root 3 and at positive root 3, we should get the locations of our two points of inflection, right? They're points of inflection because we can see that there is a change in concavity from positive to negative to positive. So, and f of root 3 and f of negative root 3 are both going to come out to be the same values, because when we raise them to the 4th and the 2nd power, they'll both become just positive versions of that same number. So negative root 3 or positive root 3 to the 4th power is just going to be 9. So it's 9, and then minus root 3 squared, or negative root 3 squared, is 3. So it's 9 minus 9 minus 48. Oh, sorry, 18 squared, or 18 times x squared. So 18 times 3, right? 18 times 3 is 54. So 9 minus 54 is going to give us negative 45 for both of those. And so now we should be able to write out all of our information here. Maybe we'll be able to fit it right here. So we had a interval where we were increasing. Our increasing intervals were from negative 3 to 0, right here, and from 3 to infinity. So we're increasing from negative 3 to 0 and from 3 to infinity. And we were decreasing on the other intervals, which was negative infinity to negative 3 and 0 to 3. So negative infinity to negative 3 and 0 to 3. And we had a local max of 0 at x equals 0. And we had a local and absolute min of negative 81 at both x equals 3 and x equals negative 3. And then we can see right here we were concave up. on the intervals from negative infinity to negative root 3 and from root 3 to infinity. And we were concave down from negative root 3 to root 3, with our only points of inflection being the 2 points, which were root 3, negative 45, and negative root 3, negative 45. So our last one here, we're just going to follow that same process. We're just going to take our derivative first, recognizing that there's no restrictions on the domain of sine x plus cosine x other than the restriction that I put there, which is from 0 to 2 pi. So to start with, we'll take our derivative, f prime of x. The derivative of sine is cosine, and the derivative of cosine is negative sine. That's also never undefined, so we'll make a note that f prime is never undefined. Then we can also set this equal to 0, which will tell us that we're looking for when sine of x is equal to cosine x, right? If we just add sine x over to the other side. Well, that happens twice every 2 pi. The increments of pi over 4 on the unit circle are the ones where sine and cosine have similar values. And in the first quadrant, sine and cosine are both positive. Right? So it's pi over 4. In the second quadrant, at 3 pi over 4, sine is positive, but cosine is negative, so that doesn't work. But in the third quadrant, both of them are negative, so that value will be 5 pi over 4. And then we won't look at 7 pi over 4 because cosine's positive, but sine is negative in the fourth quadrant. So we have 2 critical values, and with those 2 critical values, we'll just make a sine chart, remembering that we want to stop our sine chart at both 0 and 2 pi. So we'll put pi over 4 on, and 5 pi over 4 onto our sine chart. And we'll just test values into cosine minus sine on each of those intervals. And we'll start with something between pi over 4 and 5 pi over 4, something like pi. If we take the cosine of pi, that's a negative value, right? And if we subtract sine of pi is 0. So in the middle here, we're going to have a negative. If we take something between 0 and pi over 4, let's say something like pi over 6, right? The cosine of pi over 6 is root 3 over 2. And then the sine of pi over 6 is 1/2. So root 3 is more than 1. So root 3 over 2 minus 1 over 2 is a positive. And if we pick something between 5 pi over 4 and 2 pi, like 3 pi over 2, well, the cosine of 3 pi over 2 is just 0, right? And the sine of pi over 2 is negative 1. So we end up with 0 minus negative 1, which is a positive. So now we can see that our function is going to increase. Okay? I'm going to use a different color for that so we can distinguish between it being our function and our derivative. Our function increases, then it decreases, then it increases. And we'll, of course, need to figure out the values at pi over 4 and 5 pi over 4. So we'll find f of pi over 4. And so f of pi over 4 should be the sine of pi over 4, which is root 2 over 2, plus the cosine of pi over 4, which is root 2 over 2, which gives us 2 root 2 over 2, or just root 2. And then if we evaluate for 5 pi over 4, well, the sine of 5 pi over 4 is negative root 2 over 2, as is the cosine. So we end up with, this time, just negative root 2. Now, because we're given a closed interval here, those closed endpoints can also be local maxes or mins. And so we do need to figure out what f of 0 is. Well, f of 0 is the sine of 0, which is 0, plus the cosine of 0, which is 1. And we need to find f of 2 pi. Right, and f of 2 pi, well, that's going to be the same thing. The sine of 2 pi is 0, and the cosine of 2 pi is 1, so that's also 1. So we're going to have a local minimum here at 0, a local maximum at 2 pi, and a max at pi over 4, and a min at 5 pi over 4. And so we'll come back to that when we write out all our intervals in just a minute. But for now, we're going to need a second derivative. So f prime was just cosine x minus sine x, which means our second derivative should be its derivative. The derivative of cosine is negative sine, and the derivative of negative sine is negative cosine of x. So that's also never undefined. If we set it equal to 0, we end up with negative sine x equals cosine x. Well, what that tells us is we still need these pi over 4 values, but we need the values in which they have opposite signs, right? And so they have opposite signs in the second quadrant at x equals 3 pi over 4, and in the fourth quadrant at 7 pi over 4. Okay, so we'll put those two values on our sign chart along with 0 and 2 pi again, of course, just to make sure we don't go past the ends. And we'll put in 3 pi over 4 and 7 pi over 4 here. So once we've done that, we'll just test some values. Something between 3 pi over 4 and 7 pi over 4 would be pi. So if we evaluate our second derivative at pi, we have negative sine of pi. Well, sine of pi is 0, so that's just 0. And then we have negative cosine pi, which ends up being positive 1. So our function is concave up there. Remember, this is a sign chart for our second derivative. If we take something between 0 and 3 pi over 4, let's say like pi over 2, right? Pi over 2, if we take the sine of pi over 2, we get 1. So that ends up being a negative 1. Okay? And then the cosine of pi over 2 is 0. So negative 1 minus 0 is a negative. And if we take something like 7 pi over 4, something between 7 pi over 4 and 2 pi, we could take 11 pi over 6. Right? If we take 11 pi over 6, well, the sine of 11 pi over 6 is negative 1/2, so that ends up being a positive 1/2 with the negative in front. And then the cosine of 11 pi over 6 is root 3 over 2, and we can see that 1 minus root 3 is a negative, so we end up with concave down there on that last interval. And of course, we'll want to find the values at 3 pi over 4 and at 7 pi over 4, so we can see what the actual points of inflection themselves are. And so if we do f of 3 pi over 4, well, remember that f of x was sine x plus cosine x. Well, the sine of 3 pi over 4 is root 2 over 2, and the cosine of it is negative root 2 over 2, so we get 0. And the same thing happens here, except that the sine of 7 pi over 4 is negative root 2 over 2, and the cosine of 7 pi over 4 is positive root 2 over 2. So either way, we end up getting 0 there. So now we should be able to just figure out what our local minima, maxima, points of inflection, and increasing and decreasing and intervals of concavity are. We will need to take a look back over here to determine if our maxima and our minima, our local maxima and our minima are absolute maxima or minima. And so we can see that at 0 and at 2 pi, we're at 1. But 5 pi over 4 goes below 1. It goes to negative root 2. So that's going to be the absolute minimum here. And root 2 is more than 1, so that's going to be our absolute maximum. So as we write all of this out, we got a lot of things to put down this time. And we'll kind of go back and forth between the screens as we do it. But we were increasing. If we look at our sign chart for our first derivative, we're increasing from 0 to pi over 4 and from 5 pi over 4 to 2 pi. So we'll say 0 to pi over 4 and 5 pi over 4 to 2 pi. We were decreasing on the other interval there, which was just from pi over 4 to 5 pi over 4. And then we had our minima. So if we look back there, our minima were at 0 and at 5 pi over 4, with the one at 5 pi over 4 being the absolute. So we'll say we have a local min, only local min, of 1 at x equals 0. And we have a local and absolute min of negative root 2, and that one was at x equals pi over 4. And in terms of the maxima, we had a local max. The one that was only local was the one that was 1, and that was at x equals 2 pi. And we had a local and absolute max of positive root 2, and that was at x equals pi over 4. So that's everything from the first derivative. And from the second derivative, we can see that we were concave up from 3 pi over 4 to 7 pi over 4 right here. So we'll say concave up, 3 pi over 4 to 7 pi over 4. And we were concave down on the other intervals. We were concave down from 0 to 3 pi over 4 and from 7 pi over 4 to 2 pi. And then we did have the 2 points of inflection. Both points of inflections had a y value of 0, and they were at 3 pi over 4 and 7 pi over 4. So 3 pi over 4 comma 0 and 7 pi over 4 comma 0. And that is everything that we were asked for in that problem, and that is the last problem of that homework assignment. So that's it.